Hi everybody, this is Julian from Arcee. In this video, we're going to talk about training and fine-tuning. A lot of you are probably familiar with parameter-efficient fine-tuning techniques like LoRA and QLoRA, and those were a really important step forward in making training and fine-tuning more efficient. However, those techniques have some shortcomings that we'll discuss. And a few months ago, Arcee contributed to a new parameter-efficient technique called Spectrum. So in this video, we're going to start with a theoretical look at LoRA and Spectrum, and I will actually take you all the way back to Singular Value Decomposition. And then I'll show you what Spectrum is all about, why it is a better solution than LoRA. We'll look at some of the results from the research paper, and also some of my own results, which pretty much reproduce what the paper says. Okay, so no SageMaker this time, but there will be math, so there's still time to run away. If not, let's get started. To set the scene, this is really the problem we're trying to optimize. A typical model adaptation workflow involves different steps. So most of the time you will start from a pre-trained model, a good model that you found maybe on Hugging Face, maybe a model you pre-trained yourself, and you need to push it through a number of different steps to specialize it for the particular problem you want to solve. So usually you want to add some domain knowledge to the model, right? Maybe you work in financial services, maybe you work in healthcare or retail, and obviously your company has good quality data on that particular problem. So running some additional pre-training on the model is usually a first good step, right? And it's called CPT, continuous pre-training. And of course you need a data set for that. Then generally you want to teach the model how to answer your own questions, how to follow instructions, and this is called instruction fine-tuning. So starting from a question and answer data set, so Q&A pairs, coming from again your domain experts, your FAQs, your customer support, who knows, you're going to teach the model that this particular set of questions should be answered in this particular way. So it's about facts, it's about brevity or length, it's about bullet points or long sentences, etc., etc. And finally, you may want to run alignment. And alignment is a process where you start from a preference data set which contains a question, an accepted answer, and a rejected answer. And the purpose here is to teach the model that this is the preferred answer for this particular question. And a lot of times the two questions are actually factually correct. So it's not so much about getting the facts right. This is really more about tone of voice, using particular words or a particular way of answering that your company expects and your user expects, right? So CPT, IFT, alignment generally need to be run on your models. There are lots of good tools, lots of good libraries to do this. But obviously you need data sets and you need a fair amount of compute. And the larger the model you're working with and the more data you're working with, the more compute and time and budget you're going to need. And that's really the problem we're trying to optimize here. So as we just saw, building a great model, and the definition of great should be your own definition, not mine, involves many steps, and they're compute intensive and time consuming. I cannot overstate how important this is, especially if you're going to do continuous pre-training. You need a lot of data, a lot of good quality data. And for instruction fine-tuning and alignment, you need Q&A pairs. You don't need a million, but they need to be high quality, they need to be diverse, they need to represent the breadth and depth of questions that the model is likely to receive. So that's a lot of work, and I guess There are some ways around that. Synthetic data can help. Maybe I'll do a video on that at some point. But generally, this is really where you should pay a lot of attention. And this is nothing those training techniques can really fix for you. Okay, so you have to do the hard work. Now, when it comes to training, and I use training in the general sense of the word, it could be pre-training, it could be continuous training, or it could be fine-tuning. Most of the time, you have to pick between accuracy or cost efficiency, right? The traditional way to train models and fine-tune models is to do, full training or full fine-tuning, which meaning you're going to apply your data set to the model repeatedly, and you're going to update all the model parameters, right? So if you work with an 8 billion parameter model, your 8 billion parameters will be modified or may be modified by the training job. So that means they need to be loaded in your GPU memory, meaning you need to have enough GPU memory to load the model. And most of the time, you want to work with the original precision, right? And these days, most models are 16-bit, so BF16 or FP16, right? So each parameter is going to take 2 bytes, and if you have billions of parameters, that's a fair amount of GPU memory that you're going to need, right? In fact, if you work with really, really large models, they may not even fit in a single GPU, and then you need to do distributed training on multiple GPUs, and it's all kinds of fun. So it is compute heavy. It can be expensive. Long-running jobs on expensive GPU instances, assuming that you can even get them. And it's no big secret that all the hyperscale clouds these days are, pretty challenged in terms of GPU capacity. So you may not even be able to get the amount of compute that you need to get the job done, and maybe not at the price point that you were expecting. So that's a really big blocker here. So to solve that, as I mentioned before, some more efficient techniques have been introduced, and they share the same idea, which is, can we not update all the model parameters? Can we just update a subset, a fraction of those model parameters? And the idea obviously is to save memory, be able to work with smaller GPUs that are less expensive, maybe easier to procure, and generally, give you close to the quality of full fine-tuning without the price tag. So techniques like LoRA and QLoRA, which we'll double click on, are the most well known. Okay, so the idea here is we can learn only a small number of model parameters. We don't learn the full model again. We don't update the full model again. And we can apply quantization that will further shrink the amount of accelerated memory that's required. If you've never heard of quantization, I would suggest that you pause now. I've got a good video on that, or maybe go and watch it later. We're not going to dive too deep on quantization, okay? But basically shrink, let's say, the 16-bit parameters to 4 bits, okay? Well, I guess that's the 10-second explanation. There's more to it. So this is more memory efficient. You can work with smaller GPUs. You can fit bigger models in the same amount of GPU memory, and hopefully you can train faster because you're training on fewer parameters. Okay, that's the intuition. So this is quite effective for instruction fine-tuning and alignment, the later stages in that model adaptation pipeline that I showed you. So that's mostly what folks use LoRA and QLoRA for. Unfortunately, for pre-training, LoRA and QLoRA don't work very well, and we'll talk a little bit about that. So the big question is, can we get both cost efficiency and accuracy? And the spoiler is yes, and this is why we built Spectrum. But now, how do I convince you of that, right? So I could run benchmarks all day and all night, and yeah, we'll talk about benchmarks and I'll show you some numbers. But I think we need to dive deeper into those techniques, understand the theory behind them. Why can we train with fewer parameters and still get good results? And to do this, fortunately or unfortunately, we need to talk about linear algebra and matrices. Okay, so before you go and watch, dogs and cats videos instead, please stick with me. This is really important. I've tried to keep it as straightforward as possible, and hopefully this will give you, a deeper understanding of LoRA and QLoRA and Spectrum, and why Spectrum is actually a better solution. Before we actually start talking about LoRA and Spectrum, I want to talk about a technique called Singular Value Decomposition. Okay, and you will understand why along the way. A lot of the ideas behind LoRA actually come from SVD, and I think explaining SVD first will help you understand LoRA better. Singular value decomposition is a matrix factorization technique. If you took linear algebra in college, you may remember, eigenvalues, eigenvectors, and all that good stuff. That's the same idea here, except it's generalized to matrices of any size. They don't have to be square matrices, rectangle matrices, etc. Will work. So there's a geometrical explanation to this, which I don't think is quite relevant to our discussion, because as you probably know, matrices are linear transformations, and SVD breaks down that linear transformation into two rotations and one scaling operation. So you can go and watch some really cool videos on YouTube, and they have some really good SVD visualizations in there. But this is not what I'm getting at here. I think what we need to focus on is to understand that we're breaking down our matrix into a product of three matrices. Okay, U, sigma, and the transpose of V. Two of those matrices represent vectors, right? So U represent the basis vectors for column space. So basically the vectors of U are a basis, right, for column space, and the vectors of V are a basis for row space. Okay, so dimensions, right? Dimensions in column space, dimensions in row space. And in the middle we have singular values, which are basically scaling factors, right? And that sigma matrix is a diagonal matrix. Okay, so it's got zeros all over except on the diagonal where we have those singular values, and they're sorted by descending order. Okay, which is super important, as we will see, right? So that's a decomposition. It may sound a little abstract. If you want the deeper, mathy explanation, I cannot recommend enough the MIT Linear Algebra course from Professor Strang, and this is the actual video on SVD. Okay, so don't worry if you don't get all the details, right? What's important here is we have this breakdown into a product of three matrices: vectors, singular values on a diagonal, and vectors. Okay, and if you see the shape of those three matrices, you see they're identical to the original matrix, right? So in terms of reducing the number of parameters, we did a horrible job here, because now we, instead of having 1024 by 1024 parameters, we have 3 times 1024 by 1024 with a bunch of zeros. So we didn't reduce anything, okay? But that's what the next slide is all about. So the cool thing about SVD is we can use it to approximate the original matrix. So remember that sigma matrix in the middle was 1024 by 1024. We can just keep the top k singular values, okay? And k would usually be a small number, so let's say 8, right? So we keep the 8 largest singular values on that diagonal. So basically the 8 first columns, right? Because they're sorted, remember? So keep the 8 columns, throw away everything else. Okay, put zeros on top and below the diagonal. So now we have a k by k, or let's say 8 by 8 matrix. Okay, so for the product to still work, obviously U needs to become 1024 by k, and V transpose needs to become k by 1024. And so now the product of those three matrices is still a 1024 by 1024 matrix. But now you guessed it, the number of parameters is much smaller, right? Because if we sum the number of parameters for U, sigma, and V transpose, we get, 2 to the power of 10, so 1024, multiplied by k, right? That's for UK. Same for VTK, okay? So 2 times 2 to the power of 10 multiplied by k, plus the small number of parameters in sigma k, which is k squared. So if we take k equal 8, right, we have a total of 16,448 parameters versus the original number of parameters in C, which was 1024 by 1024, which is basically 2 to the power of 20, right? So over 1 million. So take a deep breath now. This is awesome because thanks to low rank approximation, we can approximate that million plus parameter C matrix with only, let's say, 16,000 something parameters, so about 1.5%, right? So now you know where we're going with this, okay? Obviously, this is an approximation, so CK is not strictly identical to C, but if we do a good job, we can get pretty close, right? And we can measure the difference between those two matrices with a norm called the Frobenius norm, right? You didn't need to know this, but now you do, right? Okay, so how about we run just a bit of Python code to show you this in action, and then we'll talk about LoRA, and you will see why you had to suffer through SVD first. Okay, so here's a simple example, and all we need is NumPy. Okay, so let's start with a square matrix, 1024 by 1024. Okay, that's what we're doing here. And we generate a random matrix here. Okay, then we compute the singular value decomposition of C, right? And we get U, sigma, and VT. Okay, and we'll print the shapes. Okay, sigma here comes as a vector, which is, I guess, optimized because we don't need all those zeros. So for the sake of working with matrices, I reconstruct that diagonal matrix. Okay, so the singular values in descending order on the diagonal and zeros, everything else. Okay, and then we keep only the top k values, and here top k is 8. Okay, same as on the previous slide. We do the same for U and V transpose, right? We print the shapes again. Okay, we print the total number of parameters. We reconstruct the C matrix, multiplying the low rank U, sigma, and V transpose, and we compute the Frobenius norm again with NumPy. Okay, how difficult is that? Not a lot. Okay, let's run this. So the original matrix has a little more than 1 million parameters, 1024, 1024. Okay, the decomposed form has U at 1024 by 1024, sigma, okay, the vector 1024, but think of it as a diagonal matrix, 1024 by 1024 with just zeros everywhere except on the diagonal, and V transpose 1024 by 1024. So now I apply my low rank, okay, and I keep the first 8 columns of all 3 matrices. Okay, so U, sigma, and V become low rank. Okay, total number of parameters is what we saw before. Okay, and when we reconstruct the matrix, compute the Frobenius norm, we get this value 291, which, you know, probably means something somewhere. I don't care. Okay, right? So just to show you that this is really what you saw on the slide, there's no difference. So let's try something. Let's try increasing the rank. Maybe if we put the rank at 64, we can see something here. Okay, so all the shapes change, but look at the error. So the error is now 263, which, you know, is a bit lower than 291. Okay, which makes sense because we kept more of those singular values. Okay, we threw away less data, so to speak, less information. So the reconstruction is a little more accurate, right? And now, obviously, if we put 1024, you can guess what's going to happen. Well, 1024, we throw away nothing, all right? We keep the original matrices as they are, and obviously the norm here is 0, or, you know, it should be 0, but it's, I guess, a rounding error somewhere, okay? So, okay, now that's SVD. See, it's not complicated. You get the intuition that we can approximate any matrix by a product of low rank matrices. And again, that rank, that common dimension, is a critical parameter. If you get a value that's awfully low, well, you throw away so much information that it becomes impossible to reconstruct. But that's how it is. If you have a high value, you may be able to reconstruct accurately, but you didn't save a ton of memory, right? You still have a ton of parameters compared to the original matrix. So that's the trade-off. Okay? Right. Now let's look at LoRA. So LoRA follows the same intuition as SVD, right? And we said when we fine-tune a model, when we fine-tune the layers, okay, we fine-tune all the parameters, okay? So LoRA says, well, I'm going to reduce the number of parameters by not training the full layer. And in fact, I'm not going to train the layer at all. I'm going to train updates only, okay? So I'm going to keep the base model, right, unchanged. And I'm just going to learn the weight updates. Okay, I'm just going to learn, parameter updates to the original model. And this update is actually parameter efficient because we learn it as the product of two low rank matrices, right? As you can see here. Okay, so we are not fine-tuning the full layer at all. We are just learning the product of two low rank matrices, and that's a smaller number of parameters. And again, why this works is exactly why SVD works. Okay, it's an approximation, and R is the critical parameter here. So this is straight from the paper, so just a more mathy way to say it, right? So for a pre-trained weight matrix W0, size n by m, we constrain its update by representing the latter with a low rank decomposition W0 plus delta W, right, the update, where delta W is B times A. B being an n by R matrix and A being an R by M matrix. Okay, and the rank, the common dimension to A and B, is a really small value. Typically, I would say 4 to 32, right? That's what you will see in a lot of LoRa scripts. Okay, and once we're done training, we still have the base model, and we have what's called the adapter model, which is the weight updates for all the layers. And when we want to predict with the fine-tuned model, we load the base model, we load the adapter, we apply the updates, and voila. Okay, so we still get one model in the end, same size, same inference latency, same memory consumption, etc., etc. And that's pretty clever, right? So again, we save a ton because we are not training on n by m parameters. We are training on r, or nr plus rm, which is really r times n plus m. Okay, so if r is a really small value, then this is really tiny. And typically LoRa will train, 1% or sometimes less of an original layer. We don't usually apply LoRa to all the model layers. This is actually configurable, but most of the times, again, if you look at the examples, you will see LoRa is mostly applied to the attention layers, right? So we're fine-tuning the attention layers on this particular data. And again, the intuition is the attention layers are the ones who pick up the relationships between the tokens, right? The proximity, etc. So these are the ones that need to be fine-tuned. You could apply LoRa to all the model, but generally, again, it's mostly attention. This is really, really easy to use. There's a good library from Hugging Face called PEFT, which means parameter efficient fine-tuning, and you can just run this stuff in a couple of lines of code, and you may even run some of their existing scripts. So just point at the model, point at the data set, and you're good to go. So LoRa, again, has become extremely popular. There's a variant to LoRa, which is called QLoRA, and the Q stands for quantization. And so we do exactly this, except first we quantize the model to a smaller data type, right? So if you have a 16-bit model, you will load it in maybe 8-bit or 4-bit, okay? And then apply LoRa. So it's the exact same process, but as you can guess, if we shrink from 16 bits to 4 bits, we save even more GPU memory, right? So that's why QLoRA has become a super effective and inexpensive way to train large models on small GPUs. However, LoRa has a number of challenges. So first one is, it might not be obvious to decide which layers to apply LoRa to, right? Like I said, mostly we do attention layers, but sometimes that's not enough. And if you do all layers, maybe you're wasting time, maybe you're hurting the model. There's a choice here which is not really obvious to make. Another one is LoRa comes with a couple of hyperparameters. The most important one is the rank, as we saw. And picking that value might not be super obvious. You'll see a lot of scripts that use 16, so should you use 16? Or, what do you gain if you use 8? What do you gain if you use 32? There's still a bit of a trade-off here between, accuracy, training time, etc., etc. So, hyperparameters are a bit tricky. Keep in mind that the rank is really telling us, how many dimensions or directions we're going to keep when we train the model. Okay, if you look at those matrices as linear transformations, if you have 10, 24, columns, then it means you have a 10, 24 dimension space. And if you use r equal 32, then you're only keeping 32 dimensions of the original space, right? And fine-tuning only in those directions. So if you take a value that's too small, you're throwing away too much information, right? So literally you may underfit the data. You may not learn the data correctly. And you may also potentially cause catastrophic forgetting, right? And just hurt the original knowledge that the model had. If you have a high rank, well, not only won't you save as much GPU memory, but you may also be fine-tuning the model in dimensions that are not so relevant, right? Or could be noisy, and maybe you could be overfitting. So again, picking the value is all about compromise. And one thing that always nagged me is, why would the same rank work well for all layers? I don't know. I don't have any data to back that up. It's just a question mark, especially for large models, 80 layers or something. We're told that different attention layers are going to learn different patterns, etc., etc. Well, then, why would the same rank work well all over? A bigger problem that was detected more recently is that although LoRA does a good job at fine-tuning, it does not do a good job at pre-training. So another way to put it is, if you want to inject new knowledge into the model, right? Teach the model a new domain that wasn't really present in the original base model, LoRA and QLoRA are not going to work well. And our team actually wrote a blog post on this. And last but not least, a more recent problem was highlighted in this paper called LoRA versus full fine-tuning, an illusion of equivalence, which is really, really interesting. I encourage you to take a look. And this actually looks at the dimensions present in the fine-tuned models. So comparing a fully fine-tuned model with a LoRA fine-tuned model. And what the main finding in the paper is that the LoRA fine-tuned models have what they call intruder dimensions. Okay, so remember those singular vectors, right, which are the basis for row space or column space. Well, LoRA models have net new dimensions, okay, that did not exist in the original model. So does this explain why LoRA can fail sometime? Does this explain why LoRA models tend to forget? So now let's talk about Spectrum. So Spectrum makes a very different hypothesis, okay? It's still trying to reduce the number of parameters that we train, but Spectrum says that not all the model layers have an equal contribution to the output, okay, and to the quality of the output. So it defines a signal to noise ratio for layers, okay? This is identical to, amplifiers. If you have a very high signal to noise ratio, it means the original signal comes out amplified with very little distortion. If you have low signal to noise ratio, then it means your output signal, is dirty and sounds like crap. So same intuition here. If that assumption holds, let's identify the layers that do contribute very highly to the quality of the output, okay? And let's run full fine-tuning on these, okay? So no parameter reduction on those, no quantization on those, full fine-tuning on these high-quality layers. And the other ones, we don't even touch, okay? So we leave them as is, no updates whatsoever, okay? All right, so now let's look at that signal to noise ratio. And this takes us back to our singular values, okay? So for each layer, we run SVD, okay? Let me show you SVD again for a second. So for each layer, we run SVD, okay? Which gives us this decomposition, okay? And we'll have all those singular values on the diagonal, okay? In descending order. Remember? Okay, let me go back to Spectrum. Once we have the singular values, we want to look at their distribution, okay? Because the intuition is, if for a given layer, some values are much, much higher than usual, right? Put big quotes around that, then it means the particular dimensions that those values correspond to have a disproportionate influence on the output, okay? And of course, we want to keep those because if those dimensions are particularly important, then these are probably dimensions we want to fine-tune and adapt to our new domain, right? And on the other hand, very, very small singular values have little influence, right? This particular dimension in the embedding space has, very tiny, negligible influence, so it's probably not worth fine-tuning this, right? So that tells us which layers we should pick, because if a layer has a lot of unexpectedly high singular values, it means it has a very strong contribution to the output. What do I mean by high? We need a threshold, okay? So the threshold is given by distribution, a statistical distribution, which has an insane name, I'm sorry for this. It's called the Marchenko-Pastur distribution. And this distribution gives us the bounds for typical singular values in very, very large random matrices, okay? And so they're called lambda minus and lambda plus, and they only depend on the size of the matrix, so number of columns, number of rows, and the standard deviation of the singular values for that matrix. Okay, so very, very simple thing to compute. So what we're looking for is the very high singular values. So we set the threshold to lambda plus. So any value that is larger than lambda plus is, you would say, outside of the distribution, right? To the right, I guess. And so it's likely to be significant, right? Anything between lambda plus and lambda minus are considered, random or, usual stuff, right? That's my math definition of it. Anything far to the right, higher than lambda plus, is a signal, right? It's a high value, it contributes heavily to the output, we should keep it, okay? So now, the signal to noise ratio is very simple to compute for a given layer. We split the singular values between the ones that are lower than the threshold, and we sum them and put them on the denominator, and the ones that are higher than the threshold, and we sum them and we put them on the numerator, and we compute the ratio, right? So now you can see if a layer has a lot of very high singular values, it will have a higher sum on the numerator, and it will have a high signal to noise ratio, okay? And this is the definition of the SNR. So how does spectrum work? After this mathy explanation, it is dead simple. The code is actually very simple. So for each layer, we compute the singular value decomposition, okay, which gives us all the singular values. We compute the threshold, okay, so epsilon, based on the layer size and the standard deviation of its singular values. We split the singular values between the high ones and the low ones. We sum them, compute the ratio, and we do this for all layers, okay? Once we've done this for all layers, we decide to keep only the layers with the highest signal to noise ratio, so typically 25%, okay? And then Spectrum will output a config file, a YAML file, with the list of those layers, and that list of layers is what we're going to use in our training script, okay? So when we run the fine-tuning job, we will start by freezing all the model layers, and we will unfreeze the top signal to noise ratio layers, okay? And we'll run full fine-tuning as usual, but only on those top signal to noise ratio layers, okay? So pretty complex math explanation for a very simple process, actually. I encourage you to take a look at the code, and you'll see exactly this happening. It's 1 or 2 pages of code. It's actually very simple code, but you have to understand why this works and what the intuition is, right? If you see for a layer high singular values, it means those dimensions, right, have a disproportionate contribution to the output. And so these are the ones you want to fine tune, and not the other ones which have a negligible impact. Okay, which is a very reasonable split, right? And then, of course, because we run full fine tuning, we make no compromise on low rank or quantization. We give those important layers the full fine tuning treatment. So hopefully, they were important before, and they'll still be important in the fine-tuned model. So using Spectrum is very simple. You can go and read the research paper. Please look at the code. Like I said, it is pretty short actually, and using it is super nice. Using it is very simple. Just run spectrum.py with the name of the model, which can be a model on Hugging Face or a model you've already downloaded. And what's the percentage of layers you want to keep. Okay, so on the first run, if you run this on a model that you haven't worked with before, Spectrum will actually compute the signal to noise ratio for each model layer, right? And you see a file that looks something like this on the left, right? The list of layers and the signal to noise ratio. And then if you said, hey, I want to keep, let's say, 25%, you get that YAML file with the list of model layers that need to be unfrozen. Okay? So what do you do with this? The easiest way to work with this is to actually run fine-tuning with Axolotl, which integrates Spectrum. So you literally copy-paste that list of layers into your configuration file. But if you want to run this with PyTorch or Hugging Face, there's just a function. You'll find it in the Spectrum repo to unfreeze the appropriate layers. Okay, so that's all there is to it. So what are the results? Okay, let's look at benchmarks. So these are benchmarks from the research paper, Mistral-7b. So here we compare QLoRA light orange, Spectrum 25%, dark orange, Spectrum 50% red, and full fine-tuning pink. Okay, and we benchmark the fine-tuned models on mostly reasoning datasets, Arcee, HelloSwag, MMLU, etc., and the math dataset, GSM-8K. Okay, so if we look at them one by one, we can see on Arcee that so full fine-tuning is still the best by a small margin, and Spectrum 50% is very close, and definitely higher than QLoRA. If we look at GSM-8K, Spectrum is very good. Make a note of that because we'll see that again. And QLoRA, it does actually pretty poorly. If we look at HelloSwag, we can see Spectrum 25%, Spectrum 50% actually, head-to-head with full fine-tuning, about the same on MMLU. Although we are not running full fine-tuning, we're running 25% to 50% of fine-tuning here. We get equal or even better results sometimes, and definitely much better results than QLoRA. Same benchmarks for Llama-3.1-8b, and I would say very, very comparable results, right? We can see that Spectrum 25 is extremely competitive with FFT on most benchmarks. And again, on GSM-8K, we see QLoRA doing a terrible job, unfortunately, and Spectrum doing better than FFT. So I'm sure there's a good reason for that. Maybe it's a math benchmark, and math, I guess, is more sensitive than language. Language is a bit subjective, but math is right or wrong, and maybe the approximation in QLoRA is actually hurting accuracy. Who knows? So these are from the paper. Go and read them. They also published some RAM usage and training time. Okay, on Llama in this case. So if you look at table 1, this is distributed training on Llama 3.8. 8b. So you can see that memory usage is pretty competitive between Spectrum and QLoRA. And if you look at single GPU usage, you see that QLoRA is doing actually better. But Spectrum still enables you to train models that wouldn't fit in the GPU if you were doing full fine-tuning. And if you look at training time, you can see that Spectrum 25 is actually faster than QLoRA. Spectrum 50, is close, and definitely faster than full fine-tuning. So you see, you get, I hate to say the best of both worlds, but you get training speed, you get reasonably good memory efficiency, and you get better accuracy, right? So I tried to reproduce those numbers, and I put a huge screenshot to prove it, running those fine-tuning jobs on different configurations. So I use SuperNova Lite, which is a Llama-3.1-8b. I used a single GPU for each one of those jobs, one epoch, batch size 1, and I fine-tuned the model on the Alpaca dataset. Okay, and I use Axolotl and the Eleuther AI evaluation framework. Okay, and those two commands that you see here are really all that you need. So if you want to reproduce this, no big deal. It doesn't take a ton of setup. I'll probably put all my config files on GitHub somewhere and put it in the video description if you want to play with this. So what do we see? So full fine-tuning, no luck. Llama-3.1-8b doesn't fit on the GPU at all. I can't even load it for fine-tuning, so out of memory error. So LoRA, I used a rank of 32. Training took 48 minutes. And you can see the MMLU, GSM-8K, and HelloSwag benchmarks. Okay, they are what they are. Then I run QLoRA, so quantizing the 16-bit model to 4-bit, still using R = 32, training a little faster. Obviously, significant reduction in GPU RAM usage because 4 bits take less space than 16-bit. Benchmarks are interestingly a little higher than LoRA, which I have to say I didn't completely expect. Okay, so well done QLoRA. And then I run Spectrum 25. Okay, so keeping only the top 25% layers with the highest SNR. So training time is 32 minutes, which is 31% faster than QLoRA. GPU RAM is a little bit higher, but it's only 22%. It's not crazy. So I could still fit models in there, and even bigger models. The MMLU score is higher. The GSM-8K score is much higher. So again, there's something here, right? There's something here on math, clearly, because it appears all the time. So it looks like QLoRA on math datasets is not a really good idea. And full fine-tuning probably captures, the finer-grained relationships that needs to be captured for math outputs to be exact, right? And that's a huge difference, 12%. I actually ran it twice to double check, and I got the same result. And HelloSwag is a little higher too. And then, just for the sake of completeness, I also ran Spectrum 50, which didn't improve on Spectrum 25, right? Close, but no cigar. So as you can see here, Spectrum 25 is much faster than QLoRA, right? And although I run only one epoch, imagine saving 31% on long-lasting jobs. That's a ton, right? 24 hours become 18 hours or something. 16 hours. 3 days become 2 days. Those are huge savings, right? Huge savings. And you get better accuracy. So that's pretty cool. So looks like you can actually get the best of both worlds here. As you can see, Spectrum is a really interesting technique. You literally get the best of both worlds, cost efficiency and accuracy. And if you wondered why RC models are that good and why we keep scoring very high on the Hugging Face leaderboard, well, Spectrum is one of the reasons. So go and read the research papers, review the slides. You'll find everything in the video description. Maybe run some of your own tests. But hopefully this will convince you to use Spectrum, and now you also have a good understanding of why this works, right? Because benchmarks are benchmarks, but understanding the theory sometimes is actually really useful, and you have to dive a little deeper. And we certainly did that today. Thank you very much for watching, and until next time, keep rocking.